and the presentation should be visible. Can someone please confirm? Okay. Yes. Okay, so welcome to the third in-session presentation that we prepared as like introduction to the Hack9. In last two sessions that were held yesterday and the day before, you were able to see, let's say, the hardware part of the preparation for Hack9. So how the team built the hardware part of the sensors and the case, 3D printed the case in which they're placed. Today, Igor and myself are going to talk about the software part with the focus on the cloud part. So we will explain how exactly the data is flowing from the sensors and ending in the data lake. The data lake that will be available to the contestants, to the teams that are going to compete in the Hack9, and from which they are going to pull data and do something with it. So you can see there is one additional name here, Stankovic. He was also, it was planned for him to be part of this presentation, but unfortunately he couldn't join us today. So Igor will cover the part that Vuk was going to present. So let's start. First, just a short look back about the hardware and the two previous presentations. So this is the sensor. These are the sensors. This is how they look like, the ones that we prepared. So three sensors connected to Raspberry Pi and with Wi-Fi connected to our Liva9 network, and they're running in our offices or outside of our offices, somewhere on the terrace or on the wall, on the outside wall. And now, so after we had this and we had some small Python script running on it that was really reading the correct concrete values from the sensors, then we had a task to somehow get those values outside of that Raspberry Pi and send it to the cloud and gather it over there inside a data lake. So how we did that? So we just extended the Python script that was reading values from the sensors. And we used two libraries. You can see the comments, how you can install them and their names. So these are basically SDKs, IoT SDKs for AWS and for Azure. They're really easy to use. So you just have to install them in the repository. You have to import them. And you can basically configure them in 2 or 3 lines of code. For AWS, you have to provide the endpoint to which you are sending the data, and you have to provide a certificate or private key file just to like authenticate and authorize yourself to communicate with the cloud. And after that, you can see how you can send data to AWS IoT service or Azure IoT Hub service. So it's just a matter of one line publishing to a specific topic. Topic is like just a string that defines to which topic the message should end up in, and the message content itself. Very similar here for the Azure. You just have to like build object that represents a message for Azure. For AWS, it's just a string message. And on the right, you can see how, in this case, JSON message that we are sending looks like. So it has time in which it was created, the location of the sensor from which it's originating, the name of the sensor, which is in our case, the name of the city where it's located. And then the measurements for particle density in the air, temperature, pressure, and also humidity. So this is the message that we are sending out from the sensor and that we want to end up in the cloud to be stored. And on the left, again, this is a really simple way how to send that message into the cloud. So you can see that we are using cloud services, AWS IoT from AWS cloud provider and Azure IoT Hub for Azure. Basically, these are cloud native services that are intended exactly for this purpose. So to connect your device with the cloud and to create a flow of data, which can be only one way, but it can also be bidirectional. So you can also send back messages from the cloud to the device. And you can also use, there are also features that allow you to monitor the device itself, to configure it, maybe to upload a new version of the software on it, and so on. So it's quite powerful. This Python script that includes reading data from the sensors, but also code that sends to the cloud services is available on this link. You also have a QR code, so you can also check it out later. So regarding now how the cloud side of all this flow looks like. So the main thing, we are sending data both to AWS and Azure, but the main thing was built on AWS, and you will see later there are also some small apps and UIs that we built, which are consuming this data in the end and showing it to the possible end users. So I already mentioned for AWS, for connecting devices, we are using the AWS IoT service. This is a completely serverless service, so it's you pay as much as you use it. If you are not sending any messages from the device to the cloud or other way around, you won't pay anything. So you're paying per message received or sent, per rule executed. You will see what the rule is later, and you're paying per million of these operations. So later you will see exactly how much we are paying for this service, and you will see that it's really affordable. It supports both HTTPS and MQTT protocols. So it's we are using in our case MQTT as like one of the standard protocols for IoT, and it has SDKs for really various languages. As you saw, we were using SDK for Python. It's like SDKs are really easy to use. As you saw, in total we had like 4, 5, or 6 lines of code to send something to AWS IoT topic. So it's really easy to be used on the device side, but you will see the same thing applies for the cloud side of the whole flow. And one really important thing is that AWS IoT really nicely integrates with various other AWS services. This means that you can, with just a couple of clicks in AWS Console, pass on the messages that you got from the device into the AWS IoT service. You can pass it on to various huge list of other AWS services, so you can do something else with them, process them, or whatever. And this is the list of those supported IoT integrations. So you can see here and recognize most of the most important AWS services. So you can basically directly store data into some database. You can send them to queue. You can store them in S3 bucket and many other things. In our case, we used 2 of these integrations. First one is integration with Timestream database. I will talk about that database or data store a bit more later and explain what exactly it is. And the second integration that we use is integration with Amazon Kinesis Firehose in order to store data, to transform data a bit, to partition it, and to store it in S3 bucket in a form of to basically to create a data lake, as I said, that will be available to Hack9 teams to pull data from there and to do some data engineering or data science on top of it. So, as I said, we use two integrations. So I will first explain the one with Timestream, and later the one that goes through Firehose and ends up in S3 bucket. So here on the left side, you can see the device part of the solution. So there is a Raspberry Pi with Python script running on it. That Raspberry Pi is connected to Wi-Fi and has internet access over it. And on that device, we placed a certificate or a private key that we use to authenticate to the AWS IoT service. And we are communicating with AWS IoT service by using the MQTT protocol. So we are sending the MQTT messages. To where we are sending MQTT messages so they end up in AWS IoT? Well, we are sending it to AWS IoT endpoint. Each AWS IoT account instance, let's say, has its own AWS IoT endpoint. So it's like a URL to which you send the MQTT message, and then basically through that endpoint, it enters the AWS IoT service, and then it becomes available to you. Later on, I will show all this exactly details in AWS Console. So you will see how you can configure how the screens look like, and so on. This is just like a graphical representation of the whole flow from the device up to the end user. So once this JSON message through as MQTT message ends up in AWS IoT, it also ends up in, it gets assigned to a specific IoT topic. As you saw in the snippet of the code from the device, at the moment when we are sending the MQTT message to AWS IoT, we have to specify to which topic we are sending that message. So that's basically like, it's like in any other message broker. It's here I would more call it like a tag or a label on top of a message which gets assigned. Of course, there is an implementation in behind in AWS IoT core that handles that and splits those messages in topics. But so this message ends up in a specific topic, and then to that topic you attach a rule. This is this part here. So this part which is rounded with this dashed line or square, it's what happens with the messages after they reach the AWS IoT, so after they appear in the cloud. So basically, we define a rule, we define we attach that rule to a specific topic, and inside that rule, we define what should be done with the messages that end up in that topic. So rule defines where the messages should end up from the topic, where they should be sent. So in this case, we created a rule that says, please store all the messages from our air quality topic inside the Timestream data store. It's quite simple. What you can do also inside the Timestream rule, you can define a query to further maybe, if you need, filter the data that ends up in the topic. So you can choose maybe to ignore some of the messages and make them not end up in Timestream, or to transform them in a way, or to get subset of the data from the message itself and store it in Timestream data store and so on. So basically, we created a flow. Each message which is created on the hardware sensor, which ends up in the cloud, in the end also ends up in a Timestream data store. And that happens from each sensor, each 1 or 2 minutes, depending on the configuration. So each one or 2 minutes from one of the sensors, a message comes in and ends up in the Timestream completely automatically by using the AWS IoT. And then over there, it's available for us to further processing or whatever we want to do. What we did for our, let's say, proof of concept here, we created one Lambda that basically queries data from Timestream for all the sensors that are out there. It groups the data per sensor, and it gets average measurement values in last 15 minutes. So for each of the sensors from Yash, from Amsterdam, from Novi Sad, for example, you get average of air quality metrics in last 15 minutes. And because we are using Timestream and we are as a data store intended to be used for frequent time-based, connected data metrics, then it's quite easy to, by using just one query, to achieve that. And we expose that Lambda through API gateway, and then we get a nice REST endpoint, which we can call and get average air quality metrics per city for average values in last 15 minutes. And as I said, later on, Igor will show you what we did or what he did, and also work with data that can be acquired from that endpoint. Now, a bit more about the Timestream service on AWS, or Timestream Data Store. Under quotes, you can see the official explanation from Amazon what Timestream is. So it's fast, it's scalable, it's fully serverless. It can really store huge amount of data. As you can see, they are saying trillions per day, and it's really fast. With that amount of data, you can really quickly store, but also retrieve and query data over there. And it's intended for time series data, so data that's connected to a specific timestamp, to a specific moment. So you can see the example. So far in Timestream, we stored 2,003,082 and some more messages or records, sensor records. So more than 2 million, and the number is constantly growing, a couple of tens of thousands every day. And so far for this service, we paid only $1.72. So this is for 3 months. It includes both storage costs, and also costs of executing queries, transferring data in, and transferring data out of the Timestream data store or service. So it's quite affordable and cheap. The main thing is it's serverless. So at the moment while we were still experimenting and not using it, we were not paying anything for Timestream. So it's not something like AWS RDS. You spin up an instance and you are paying for specific size of the instance constantly, even if you are not using it. And on the image below, you can see how the representation how one of the representation through which I tried to show how data is stored in AWS Timestream. So each record in Timestream is basically a measurement, and you can see that each measurement has a name. So here we have example of several measurements. One is PM10, so one of the particle size value. We have location also as a measurement. We have a temperature as a measurement. And then each measurement has one of the measurement values of a specific data type assigned to it. So for PM values, it's a big integer. For temperature, it's double in our case. For location name, it's varchar or string. So that's what you will always get. You will get a measurement name, time, the moment, the time step at which this measurement was created, and then a value of a specific type assigned to it. This is just from a query manager. I queried a single record, so it's displayed like this. That's why there are some, let's say, null values or missing values for example, for PM10, it's missing varchar or double. It's because of the representation. It's not stored like that in the data store itself. It's just how it's represented in the UI. Along with that, to each measurement, you can add something that they call a dimension. It's, let's call it like a metadata. So in our case, to each measurement, we added from which locations, from which coordinates it originates. So this measurement has a name and a value and a time when it was created, but it also, because of the added dimension, it has coordinates from where it originates. It has name of the sensor from which it's coming from, and the name of that sensor. So this is the ID of the client that sent this measurement, and this is the name of the sensor that sent that measurement. Because theoretically, on one sensor which has one name, we can have multiple sensor clients which are uploading. That's what we wanted to support. So that's why there are here two values. So that's how data is represented. And then how you can query the data. Well, it supports SQL. So it's really easy. You don't have to learn a new language. So this is exactly the query that we are using in Lambda to expose data through the API gateway as a REST endpoint. So you can see it's getting all of the measurements, like creating a pivot table, grouping per sensor name and location and coordinates. And also what is highlighted is it says time should be between now and 15 minutes ago. So by only saying this and applying this average function, we are getting average measurement values in last 15 minutes. So you can easily say, give me averages for 30 minutes. Or if you say just 1 minute, then you most probably will get just the last measurement and so on. So it's not a relational database, it's no SQL, it's time series optimized, but again, it's using SQL. So it's really, learning curve is not steep at all. So this is one flow that we implemented. The second flow that we implemented, as I said, uses Firehose and S3 bucket. As you can see, up to the IoT topic, everything is the same. And in fact, it's the same implementation. The same thing happens here. So the same message ends up in IoT topic. And then there is additional rule, new rule that is attached to the same topic. So the message that comes into the topic that then is basically branched from the rule. And one ends up in Timestream. And the same one also ends up in Kinesis Firehose. It's transformed by Lambda and stored in S3 bucket. So in this case, we used a rule, AWS IoT rule of type Kinesis. So we say, please use this message and also send it to Kinesis Firehose. Kinesis Firehose can do some kind of transformation with provided Lambda. In our case, we transformed basically a JSON message into the CSV format. And the Lambda itself also prepared partitioning data, information on how data should be partitioned. I will show that in detail later. And then Kinesis Firehose basically created partitions in S3 buckets, basically a tree structure, folder structure, and stored CSV files over there. And that's, again, a flow that is accumulating data that will be available during the hackathon. So this is the complete picture. Everything, messages end up in AWS IoT topic, and from there, because we attach two rules, they go through two flows. One makes data end up in Timestream, and then you can query it through Lambda and API gateway by invoking, making a HTTP call, get HTTP call over there. And other one automatically stores everything and accumulates everything in S3 bucket in CSV format. And just a note, we used for the AWS Cloud Development Kit CDK to spin this everything up by using TypeScript language. So now a demo. So I will switch to a browser and share. Just to find the right one. I think it's this one. Just a sec. Yeah, it's that one. So now you can see the AWS Console. This is a central account, AWS account, which we are using for organizing Hack9, and where that S3 bucket as a data lake is placed. So all the teams that choose to use AWS to make their solutions, we will share access to this S3 bucket to their accounts that they get for the Hack9, with some budget assigned to it, and they will be able to pull data from that S3 bucket, maybe do some ETL magic on it, or maybe some machine learning, or whatever the idea behind it is, and yeah, do something useful with that data. But now let's talk about AWS IoT first. So this is the AWS IoT console, and one of the entities over there is called a thing. So you can here see a screen that says things. Basically, a thing in AWS IoT can represent one physical device. Here it says representation and a record of your physical device in the cloud. So this is basically like a twin of your physical device in AWS IoT. And you can see here we have how many? 8 things created, and each one of them represent one of the real hardware devices out there in Europe. You can see there is one for each of our offices, and this is one that I used at my home for testing. So then what's important, let's say, let's choose the 9 Air Amsterdam thing or device. Each of these things or devices you can assign to a group, so you can group those devices. It's like a logical grouping. You can create a device shadow to interact with the device through console. You can interact in a different way with it. I will show this also later. And what's most important, you have to assign a certificate or a key to this device, and that's exactly what we are going to use and what we used on the client side to authenticate to AWS IoT. So when you are creating a thing or a device, you have to create a certificate. Then you get download links to download certificate and keys, and then you have somehow to transfer them to your device and use them to authenticate to AWS IoT. So you are not saying, you're not defining the name of the device to which you want to send the data or anything else. You're just saying, I'm using this private key. And by using that private key, you're saying, I'm that thing or I'm that device. What else is behind this certificate is are the policies. So now if I choose this policy, each certificate has one or more policies assigned to it. And a policy defines what that thing or device that is represented by or identified by that certificate can do in AWS IoT. So you can see that we allowed the thing that is using or that represents itself by this certificate to publish messages to this AWS IoT endpoint. So this is the endpoint. And to this topic. So you can send messages only to this topic. If you try to send messages by using this certificate to AWS IoT to some other topic, you will be rejected and you will get an error message back from AWS IoT. So here we also allowed a message to be received. So we allowed the communication to be bidirectional. Also, this subscribe indicates that, so you can subscribe on device side to sensor air topic, and then you can send message back through MQTT protocol from the cloud to the device. And we were doing that for one case, but that's not in this presentation. If you're interested more about it, feel free to contact me, for example, and I can also talk a bit more directly about that. And we are also allowing, in this case, client of this name to connect to AWS IoT by using this certificate. So only client with this name that's defined when you are instantiating the AWS IoT client on the device side. In Python code, you have to say this client name in order to be allowed to connect in the first place to AWS IoT. So those are things and certificates behind them. And then basically, as I said, you are just, by using certificate, you're identifying yourself. By using certificate, you get things allowed through policy what you can do on AWS IoT, but everything else happens through topics. So you connect to AWS IoT, and you are allowed to perform operations which are defined in the policy, and to send messages to the topics that are defined over there. And then the next action is basically publish or push the message to that topic. If you have permissions to push to that topic, that will go through. So next thing is AWS IoT, AWS Console has this really nice MQTT test client support, and you can use it to test what is flowing through your topic. So you can subscribe to a topic from here. So add an additional subscriber, and basically here you will see all the messages that are coming to this topic logged. But you can also publish artificially message to this topic, so you can use it for testing. That's also why it's called test client. But if you think about it, you can also use this publish to topic to achieve bidirectional communication. So if device is subscribed also to a topic, you can come over here, send a message over here, and it will end up in the device. So what you can, in theory, achieve, you can control your device from here if it's configured to listen to MQTT messages coming in and doing something based on that. Again, just a note, that's exactly how this tunnels thing here, functionality works here. So it allows you to create SSH tunnel between your machine and your device. So you can have like SSH to the device and do something over there. So I will now resume subscription on this topic over here, and let's wait a couple of hopefully only seconds, and we should see a message appearing or arriving from one of the sensors. It shouldn't take more than a minute, hopefully less. Here it is. So yeah, sensor from Novi Sad was the first one, and we got a message at this moment. Now it's from Belgrade and so on. So messages will keep coming in. So messages from all sensors are ending up in this sensor/air AWS IoT topic. Yeah, so what we can, now when we have messages in the topic, I explained, I was talking about the rules. So we can go to the rules part of the console. And here you can see that we created two rules for those two flows. One is Timestream rule, another one is Firehose rule. So one is made to write record in Timestream service, another one is made to put a message to the Firehose delivery stream. Now just let's quickly look how the rule looks like. So the rule defines a topic to which it's attached. So it's listening, or it's triggered by the messages flowing through this topic. You can, by using SQL, as I said, filter out the messages from here, from the topic. So here I don't have a where statement. So basically all the messages from sensor air topic are are sent further. And then for a rule, you define an action. And here we defined an action of type write a message into timestream table. That's a predefined action. And when we open it, we see we defined to which timestream database it should be written, to which table in timestream database, and which dimensions should be added to measurement. So as I said, we are adding sensor as a client ID. We are adding name as a name we are sending, location name and location coordinates as a dimension to each of the measurements. So that's one rule. Another rule is firehose put rule. Again, same topic, more simple SQL statement, just everything from this topic. And it just what it says here, send it to this firehose delivery stream, nothing else. So as you can see, it's really simple to connect message from the topic with one of the other AWS services. It's a couple of clicks. Basically, you choose 3-4 drop downs, maybe write this really simple SQL statement, and that's it. Data will start ending up. Of course, you need to configure security rules, policies, and so on, as usual in AWS or any other cloud provider. But apart from that, it's really straightforward. Now a bit about Timestream. So here we have a Timestream console. We have this one database, and we have metrics for this database. We can see, and we can see which tables we have. We have only one table measurements, nothing else. You can create multiple tables. And if we go to query editor, then we can basically, this is the query that I showed, we can perform it by writing SQL, and this returns average measurement values for each of the sensors for each of the cities for last 15 minutes, and the coordinates from they came from. And you can do just select star, then you get the view that I showed in the presentation. So single, it's not now a pivot table that is done to that more complex query. This is just single measurement displayed. And what you can do also something, let's say like this, count me number of messages in last 90 days. And you will get those 2 million. So now we have even a bit more. What's really good with Timestream, data is like stored, data has a life cycle. You can say, for example, keep me data for last 2 days in memory, so they are quickly accessible. Everything else, what is older than 2 days, you can configure that time period. It gets written to a magnetic storage, which is much cheaper. So in our case, since air quality data is, let's say, maybe for this case, for our purpose, people will most likely want to know what it's today or in the current moment or in last 15 minutes or in the worst case for previous day. Then we configured to keep 2 days in memory. Everything else is transferred to memory storage, and then it's much cheaper. Of course, if you want to keep in memory a longer time period, you will pay a bit more, but as you saw, it's really, really affordable. So that's one flow, Timestream. Other flow, Kinesis Firehose. So there are some other delivery streams here, but we will use this Air Firehose one. So basically what we are doing here, we have a delivery stream. Destination is S3. There is a Lambda, which says Firehose CSV transformation. So what it does is transforms and filters, not filters, but transforms and does some specific transforming on our CSV message to make it CSV formatted. It's also like buffering data a bit, so then we don't get one CSV files with only one measurement inside, but we get one CSV file with more measurements inside. So we configure it, you get one CSV file per, I think, 15 minutes, and measurements for last 15 minutes, single records inside. and we define a destination, and we define the partitioning. So how to define the folder structure. So then if we go to S3 bucket, so you can see here, this is the S3 bucket, that's the same name. And here it's how it partitions. So from this stream, it ends up in sensor, then partitions for towns, and then partitioned per date. Let's check today, it's 12th. So you can see it, yeah, it's per 10 minutes. So in each of these files, you have measurements for time period of 10 minutes. And you can see last one was in 16:11. So at 16:21, there will be a new one created automatically. So Firehose is buffering, and every 10 minutes writing to the S3 bucket. What else? Yeah, Lambda that's using the Timestream. This is the one. It just has again a role to assign to it that allows it to read from Timestream. It has API gateway on top of it. So again, it's really simple to work with Timestream. You create a Timestream query client. You write the SQL query. You get results, and basically here we transform it from that Timestream result set back to JSON format, and we return it. And this is how it looks like. So when we invoke MPI gateway, we get JSON for each town measurements average for last 15 minutes. So as you can see, really a small amount of code written. You can really quickly configure your flow, easily connect your device to cloud, configure your flow, and make your data end up in one of the AWS services. So it gets exposed to a REST endpoint or ends up in S3 or whatever else. And as I said, we used CDK by using TypeScript. So again, it's like 20 lines of TypeScript code to create a rule or something like that. So in a couple of 100 lines of code, you can configure this whole flow and have data flowing from your device and get stored somewhere in Timestream or in a data lake in the S3 bucket. Yeah, and I think that's it. So I will stop sharing and give the word to Igor. So he will show you what we did with that data that we collected to like do a proof of concept, and he will give you some ideas what in theory can be made on Hack9 day. But so that's not what you have to make. That is just one idea. You can build something completely different based on your idea.
Yes, thank you, Miro. So I will share screen now. I hope that you see the right one. So this was Miro's last slide. Yes. So as Miro said, I'm going to show you our two use cases that we have. So one is a simple web app that can be accessed from your smartphone or from computer browser. And the other one is our Hack9 weather widget that we have on eSite.rs portal in Serbia. I will repeat what Miro said. This is just an example. This is like our ideas, what can be done with data that provides our endpoint and from data that we gathered from other publicly available sensors in all countries or all EVN countries. And also this is just a presentation. This is a React web app that can be written in one day. And I will show you how that works right now. So over here we have I will enlarge this a bit. Yeah, something like this. So this is just web app open in separate Chrome window, and the same thing we can do on our cell phones. As you can see, it's all green because today in Novi Sad the air is great, but I will later show you an examples how that will look like if we have a terrible air here in Novi Sad. So my idea was fairly simple. I want to have an application that gathers data, preferably real-time data, or at least data from within last 1 hour or half an hour. I don't want to have a map. Every other platform that you can see on the internet has map. I don't want a map. I just want colors. I want numbers, and I want a simple, let's say, a scale, like a grade of my air quality. As you can see, we're using here European Air Quality Index. More about European Air Quality Index will be available for you alongside the assignment. So you will get another document with, let's say, a starting knowledge base with some links where you can learn more about and maybe apply some of those rules that you see in those documents. So yeah, I want a number. This number goes from 1 to 100. So we are 11 up until 20. Everything is okay. I have an average data for the whole city. As you can see, it's PM 2.0, 2.5 and PM 10. We don't have a PM 1 from third-party data. Live data, what Miro said, we are connected to 9-ear sensor, which is 20 meters from me on terrace here at Live9. We are using location API, so I'm able to see what nearby stations are in Novi Sad. This is automatically translated from Serbian to English, so no, there is no station called Tequila. It is a street named Tequelia, but yeah, Google thinks it's a drink. We have other stations which are further away. Also, this is not a blush. This is also a government station that we are connected to. You can see that we are reading data from Klimerko, and we are reading data from Sežu community, which is global community. This Klimerko community is more like I don't know, Balkan-based, Serbia, Bosnia, Macedonia, and in that area. And we have a map. You can see everything is green. My current position is the black one, and others in Novi Sad are color-coded. And yeah, this is like a simple thing. No ads, no affiliate links, no interactive maps. This is just an image. And it sits on your Mac dock. And as you can see, it gives you a nice notifications. And every half an hour, it's auto-refreshed, and you can see what's the air quality in your city and in your 2 kilometer area around you. This data over here that you see will be available also on our AWS and Azure services. I have data for the whole Serbia over here, but we will have data only for Live9 cities available. I will show you Belgrade right now. We are connected to Belgrade sensor. You can see it's similar data. There were some 19s over here when Miro showed you a few minutes ago. There's a lot of community sensors, in Belgrade, and this is the whole map of everything that we have in Belgrade. Similar thing is for Zrenjanin as well, and also for other Live9 cities. Let's jump back to Novi Sad because it's easier to work with. Here is again Trifkovićev Trg. One additional thing that we have over here is explanation of what this application is all about. It's all about colors, and in my so from my perspective, this is the most important thing. Some European scales range have 7 colors, some have 6. I like five color scales, and it's really easy to remember. If it is green, everything is okay for sensitive populations and for just regular people. For yellow, it is everything okay, but yeah, it's getting a little bit worse. When you go to orange, still the majority of population should be okay, but sensitive groups may have some symptoms, let's say coughing or tears in eyes and stuff like that. And for red and purple, it's bad and you should consider your outdoor activities. Because everything is green today, I will spin up a development environment and I will show you how that will look like if not. For example, this is just, so for average for the whole city is now orange. We have a different pictograms over here. As you can see, some stations in let's say left part of the city are polluted, and this looks like this. And if we go all the way up, we can also get some purple or red notifications, and it looks like this. So yeah, you can see how this can be. So what are different representations of data? And yeah, when you see this screen over here, you will clearly get an image in your head that something is wrong and that you should pay attention. Let's jump back just to real thing. We also have 2 days of historic data over here. As Miro said, you probably want to know data today, maybe yesterday, 2 days ago, and that's it. So we have a nice graph over here, and I know that this George station is crazy. So yeah, if we have a station that probably is not positioned correctly, you will get data like this, and it's up to you to what you're going to do with this data on Hack9. Let's see what government is telling us. Government is also green with some nice spike over here. So it's a nice thing that community census and government census are in line. And the last thing for this presentation, I have images from January from this small application, and air quality in Novi Sad can be like this, so 2, which is very nice. And it can be like this, which is completely terrible. And this is one of the reasons why we have this topic, because this is something that shouldn't happen. And we need to know that this is happening, and we need to know how can we protect ourselves from this. And also a bonus image. This is from air care application on my smartphone. The same day, but it's the image of whole Serbia. That's one use case. So I'm repeating, this is not what should build. This is just an idea for a front-end part, what you can do. Next week, we'll have more sessions about what can be done on the AWS and Azure. So you will get more ideas of what you can do with the data. This is just displaying data. Another thing that we can do is that we did actually as widget on our Inside AWS portal. I will show you how that looks like live. Here it is. Here is Inside AWS, and if you scroll down a little bit, you will see Hack9 Weather. It's a carousel widget in WordPress. As you can see, it just cycles through every Lebanon city. Was Belgrade, now it's Amsterdam, and so on. That's it from me. I hope you got some nice ideas. If you have more questions, Igor Dedic from Novi Sad, you can ping me on Teams. Miro, you can continue.
Yeah, so let's first see, are there any questions? Yeah, Dmitro had some, I think I answered some of them. Yeah, there is last one to get a snapshot. Can you please, Mitro, clarify what you mean under the snapshot? So zip file of everything or just access? As I said, we will provide open access to the bucket on 23rd. So you can see the structure and everything else. If it's needed to have a zip file, I think that's also fine. We can place it somewhere on OneDrive and anyone can download it and do something with it.
Yeah, can you hear me?
Yes.
Yeah, I just mentioned that for some proof of concept of predictive modeling, it's quite time intensive process. So it would be great if we have some zip file of this 2 months of data, like to understand if we can do something with the predictions. Because if we get this data only on 23rd of May, I'm just think that it's not enough time to even get a proof of concept. I'm even not talking about something working and
yeah. So yeah, I think that's possible. That will be, as you said, a snapshot. In the end, you can use the real data directly from S3 bucket. So right, Igor, I think we can like zip what we have now and place the same zip file on the same S3 bucket and just allow public access and you can download it. Would that work?
Yeah, that would be very, very cool. Thank you.
Okay, great. So then I will do that latest, let's say Monday. And yeah, I will send basically the info to all the registered teams to take a look at that. And so if you want, you can start working something up front. Any other question? Okay. If not, then that's all for today. So the data will keep accumulating right until 27th of May. Also, it will keep coming in during the Hack9 days. So you will be able to have historical data and yeah, like a small additional info for the ones on the presentation that took time to attend. So there is data that you saw, but there is also on the same bucket data, as I wrote in the chat, from the public sources that Igor shown. So from all the countries, from all public measuring stations, it's also in a different folder. So you can also combine those two maybe. And there is also open weather data collected over there. So you can also maybe do something with wind direction, wind power on that day and so on, maybe to predict something or just display or create some cool idea. So then I think only thing left is to invite you next week to 2 additional sessions that our data experts will give. First one is about AWS and about data-oriented services you can use over there. So they will talk about which service you can use to transform the data, to analyze the data, and so on. Same thing, next presentation about Azure. So I would say if you plan to participate, and I would invite you to do that, those presentations should be really useful. So you can maybe already build, apart from the data that you will have access to, which services you can use to do something with the data. Okay, so then that's it. Thank you all for attending and talk to you.
Thank you.
Bye.
Thank you.
Bye.
Thank you. Bye-bye.
Bye.